Okay, in this lecture, we're going to be going over continuous probability distributions again. This particular continuous probability distribution that we're going to be going over is the normal probability distribution, and we're also going to be exploring z-scores. So once again, continuous probability distributions means that there are no meaningful gaps. It can assume any value. And this is really the type of distribution that you're probably most used to looking at and understanding. So by the conclusion of this lesson, you're going to be able to describe the characteristics of a normal probability distribution and describe the standard normal probability distribution and use it to calculate probabilities. So the normal probability distribution, it's a bell-shaped distribution and has a single peak in the center. It's symmetrical. It's asymptotic, meaning that the curve approaches but never touches the x-axis. In other words, it theoretically goes on for infinity. And we're going to be going over all of these, so just so you know, so don't freak out that I'm going really fast through this. But it's completely described by its mean and its standard deviation. And then we're about to go over the family of normal probability distributions. Okay. So the normal curve is symmetrical and the two halves are identical. So you have the mean, the mode, and the median all in the middle, and they are equal. Okay, and then you've got the tails on the ends, right here and right here. And then you've got the two halves of the distribution, and they should be completely symmetrical. And this tail goes on for infinity. It never touches the x-axis. So the family of normal probability distributions. Let's see here if I can zoom in a little bit. There we go. So this right here, we have equal means but different standard deviations. If you remember previously, we discussed how there are 68 about 68% of individuals that fall within one standard deviation of the mean. Well, if you have a really small standard deviation, then you're going to have a more leptokurtic distribution, and it's going to be a higher peak, and you're still going to have 68, but it's going to be up here. The peak is going to be up here. And the distribution is going to be a lot tighter. And then, so this right here is different plants. Different plants and the years of service. I guess this is some sort of industrial plant or energy plant. And so the mean is 20 with a standard deviation. The Camden plant is a standard deviation of 3.1 years. The Dunkirk plant is 3.9 years, and then the Elmira plant is 5 years as a standard deviation. So you can see as the standard deviation gets larger, the distribution gets wider. Okay, so looking at here, we have different means and we have different standard deviations. So you see we have the x-axis is PSI, the mean of maybe these are tires or something to that effect, or but no, there's no way that this is tires. Maybe this is pressure inside of the plant, containment or something to that effect. But the mean is 2000 psi with a standard deviation of 41 psi. So you've got the mean, it's lower than the next mean. So the next mean is 2107 psi with a standard deviation of 52. And you see that it's spread wider, and it's more platykurtic. This one seems more mesokurtic. And then you have this one right here that seems more leptokurtic. And the distribution's a little bit tighter. You've got a standard deviation of 26, so this is the smallest standard deviation, which means that it's going to be the highest distribution. But this also has the highest mean. So you can see, depending on the mean and the standard deviation, you're going to have different looking normal distributions, even though they are all normal distributions. And then finally, you have, down here, you have different means, but the same standard deviation. So you have sugar yummy candies, alphabet gem candies, and weight droppers. They have a mean. The candies have a mean of 283 grams, 301 grams, or 321 grams. So they all have different means, but they all have the exact same standard deviation, meaning that they all more or less look the same. They're just in different locations. So what's important, and I feel like you guys have seen that so far, and that was all just kind of a review, but what we're introducing here now is something called the z-value. And the z-value is something that's really cool, that's going to make it so that you can almost immediately interpret your results. Okay, so a z-value, essentially, you have, instead of actual values, on the x-axis, you're going to have standard deviations on the x-axis, or z-values. And so the standard normal probability distribution is a particular normal distribution. It has a mean of 0 and a standard deviation of 1. Okay, so in order to calculate a z-value, you are essentially calculating how many standard deviations your value is from the mean. The first step in order to calculate the standard deviation is you need to calculate the mean. Right here, I have a randomly generated set of numbers that fit the parameters of the previous exam. And so the first thing that we need to do is we need to calculate the mean of the previous exam. So we're going to do average. And so the average was about, well, it was about an 86, but the randomly generated numbers generated an 85.83. Okay, so then we do equals minus each value, let's see here, that is the deviation from the mean. Okay. And so in order to get to the standard deviation, we need to square all of the deviations from the mean. And then we do equals sum. And for this particular situation, this happens to be the entire population. So there are 115 in this population, so equals divided by 115, and that gives you the variance, then equals square root of 326. So the standard deviation would be 18.0775. Okay, so there's no way that 18 is right. I made a miscalculation there. I missed a 1. That is a big deal. So divided by 115, not 15. So the variance was actually 42.62. And then the standard deviation is 6.528. Okay, so then you have the population mean, which is 85.83. And then you need to divide, so in order to get the z-score, we're going to get the z-score right here. So it's x minus the mean divided by the standard deviation. Okay, so we have x minus the mean in this row right here. Then we do equals x minus the mean divided by the standard deviation. Okay, and so when I drag this up, this is going to give us our z-scores. So this z-score right here, given that we are dealing with a normal distribution, this is saying that this particular score is 1.65954 standard deviations below the mean. This particular score is 1.403819 standard deviations above the mean. Okay, so what do we do with this information? That is a very good question, and that is why I gave you all a wonderful cumulative area under the standard normal curve to the left of the z with the value z equals 0 or negative, which we can do this in several different ways, but basically you look at this negative 1.65, so negative 1.65, so you have negative 1.6, and then you go over to 5, and essentially there is 0.0495 is the percentage of individuals, or the probability of an individual being lower than this score. So the probability of an individual being below a 75 is 4.95%. Okay, so then if we look at 1.40, okay, so 1.40, 0.0808 are the number of individuals to the right of 1.4. And so in order to calculate the number of individuals who are to the left, you would take 1 minus 0.0808, because you're using the complement rule there. And so there's only about 8% of individuals who scored higher than a 95. And then once again with a 92, you look at 0.94, 0.94, so 0.9, and you go to 4. 0.1736 is the number or the probability of an individual scoring higher, and then 1 minus that is the probability of an individual scoring lower than that score. So this is a really powerful tool to be able to take a normal distribution and be able to say, okay, this score, what is the probability of an individual being above this score, and what is the probability of an individual being below this score? And any one of these scores right here, I can tell you what is the probability of an individual being above or the probability of an individual being below, based on using this this standard normal curve. Okay, so I'm going to open my PowerPoint back up. So there are lots of different ways. The one that I gave you guys, like I said, you've got to look at the shaded area. The shaded area is the probability. Anytime that you see shaded area, that means that you're calculating that probability. So this right here is just dealing with the negative side. But you can use this, if you understand what you're looking at, you can use this cumulative area under the standard normal curve to the left. You can use this to calculate because it's symmetrical. Okay, so you just have to reverse it in order to get the area to the left. Okay, or use the complement rule to get the area to the left. So right here is a slightly different one. This right here, this one that we see here deals with the area to the right of the mean, and so you see right here, if we have a 1.5, so let's go down, let's see if, or 1.403. So 1.403, this is the number of the individuals, or the probability of an individual being between the mean and, being between the mean, and the 1.403. Okay, this is the probability of an individual being between the mean and a z-score or 1.3 standard deviations above the mean. Okay, so depending on the chart that you're looking at, you've really got to know what chart you're looking at to determine what is the probability of an individual being above the mean, below the mean, or the number of individuals being below them entirely, the number of individuals being between a certain range. But you can use virtually any of these probability tables to give you the information that you want. You just got to really know what the table's saying. Okay, so when we say the shaded area, we're only talking about this area right here. Okay, so if I say what is the probability of an individual falling between these two numbers, you've got to be able to tell me what that is, and we'll do some exercises with that. So we've got the empirical rule, which we've talked about earlier. With the z-scores, remember what I said about individuals falling within one standard deviation. There's 68% of individuals falling within one standard deviation, 95% falling within 2 standard deviations, and almost all people falling within 3 standard deviations, but it's really actually only about 99.7, or to be more specific, 68.26 falls within 1 standard deviation, 95.44 falls within 2 standard deviations, and then 99.74 falls within 3 standard deviations. Okay. Okay, say I want to determine the number of individuals that fall within a certain range. Okay, so say I want to look at the number of individuals that the probability of an individual being between 1 and 1.25 standard deviations above the mean. Okay, so I find I said 1 and 1.25. So the probability of an individual being 1 standard deviation above the mean. So we take 0.5 is the individual being above the mean. So equals 0.5, and then minus 0.1587. Okay, so that is the individual being 1 standard deviation above the mean. And then I said 1.25, so 1.25, so we've got 0.106, or sorry, that's not 0.106, 1.25, 1056. So we've got 0.5 minus equals 0.5 minus 1.056, and that's 39.44. So you just need to do equals 39.44 minus 34.13, and there are a total of the probability of being between 1 and 1.25, or having a z-score between 1 and 1.25 is 0.05 0.31 or a 5% probability. Okay. What is the probability of an individual being between 0.5 above and 0.5 below the standard deviation? So right here you have 0.3085, so equals 0.5 minus 0.30 minus 0.3085. Okay, so 0.5 below and 0.5 above, you would actually just need to multiply this by 2, equals times 2. And the probability of being within a half of a standard deviation of the mean is 0.383, or 38.3% of being within a half of a standard deviation of the mean. So what I would highly suggest you do is play around with this this sheet. I will give you this sheet, this exact sheet, for the exam. And so if you run into a problem like this, you will be able to utilize this exact sheet. You don't have to put this sheet on the note card. You just have to know how to use this sheet. This sheet is a tool, and you have to know how to use this tool. And this tool will, always be accessible to you. But if you don't know how to use it, it's just a piece of paper. So that is the normal distribution with the z-scores. Hopefully this has been beneficial for you. And yeah.